Okay, so at this point, we've set aside the static region of our terrain and passed that to the render object, and now we can do a more detailed fracture on this area that we're actually interested in here. Now, we don't necessarily want to include the entire volume of this entire region for our detailed fracture. Oftentimes when you're doing destruction work, you want to remove some of the interior volume because sometimes it's just too much material that's being thrown around and it just doesn't look very nice if you use all of the volume. That's not a rule. Certainly in many cases, it's fine to use the entire volume, but I have found it to be very common that I do want to remove some of that inner material there. So to remove some of that here, I'm just going to isolate the top portion of this terrain. So let's drop in a blast sop from the first output of our split here. That's the split that's setting aside the piece that we're interested in fracturing. And on the blast sop, I'm just going to select the inside group. This inside group is conveniently created for us by that Boolean fracture that we did earlier. And now I'm just going to use this top portion of the terrain as a cutter object. So let's drop in a transform and move this down a bit in the Y direction. Let's display that and template display the original piece. So now we're just going to use the top portion of the terrain to cut out a slice of the ground here. However, this slice isn't quite big enough. It's not going all the way through the object here, and that can cause some real problems when you're fracturing. You always want to make sure that your fracture cutters are passing all the way through the geometry everywhere. So let's just drop in another transform sop. Actually, we'll just use the same one here, and instead of using the pivot transform of 0, we're going to tell this to pivot around the centroid for its rotations and scaling. So I'll just use my centroid transform preset, which is just setting that pivot to the center of this object. And I have to once again set this downward Y translation. And now I can also turn up the uniform scale to make this piece go all the way through the geometry that it's cutting. And we don't necessarily want this to be a very smooth cut through the surface. We want to noise this up a bit. Let's noise that up with another mountain sop. Drop in that mountain and increase the height a bit. That's too high frequency, so we'll turn up the element size as well. This looks like it gives us some pretty nice jagged detail. That looks like a pretty realistic noise pattern for that interior cut. And now that we have this nicer cutter plane, let's do another Boolean fracture. We'll connect this entire chunk to the first input, that noisy cutter into the second. And for this one, I am going to turn off this detriangulate option. I'm going to set that to no polygons. So now you can see that the output of that Boolean fracture is entirely made of triangles if we display wire on shaded. And this will help to ensure that we don't have fracture issues later that are caused by the detriangulation messing up the mesh and making it less clean for fracturing. I mentioned earlier that I didn't detriangulate in this first Boolean fracture pass because I didn't really want to triangulate this entire rest of the terrain here. It's not really a problem to triangulate this, but I'd rather keep it clean as is, as long as it's not causing problems. So there's a small risk here, but that was a very simple initial cut, so figured I would just give it a try. But now as we're doing more fracture processes, and we're just focusing in on this area of interest, I'm keeping detriangulation off, because here I'm not really worried about over-triangulating a massive portion of the mesh. This is just our detailed area of interest, and I want to make sure that all of this will be fractured properly as we do these multiple passes. So now that we've done this extra Boolean fracture with this noisy cutter here, we can just delete this section on the bottom of that chunk. So I'm just going to once again go into my selection mode, make sure we're selecting prims, and we're going to select based on the name attribute once again. I'll just select this piece on the bottom of that chunk, hit delete to remove that, and now we can generate some nice detailed cutters to do a detailed fracture on the rest of the surface. So to generate all of the cutters to chop this up, I'm just going to first drop in a null here to keep things nice and clean, and we can just do a scatter onto the surface. By default, this scatter will create 1,000 points, which will be more cutters than we're going to need for this. I'm going to start with a small number as we're setting this up, and then you can increase the number of cutters for more detail. So I'll just start with 5 points here. Let's make that a bit bigger so you can see them. And I'm just going to instance some grids onto all of these points. And just to randomize the direction of those grids, we're going to set a random normal attribute. So drop in an attribute randomize, set the name to normal, and the distribution type will be direction or orientation. Now we'll drop in a grid and a copy to points, and connect the scattered points to the second input, the grid to the first input, and now we have some cutters starting to take shape. They're pretty small though, so let's template the piece that we're fracturing here. And we always want to make sure that the cutters go completely through the geometry. So what I usually do here is I will make the grids much larger than is really necessary, and then after they're scattered, I will trim them down to the area that we really need, and then I will add some more detail after that. So let's start by setting a really large size on these grids. I'll do something like 150. Let's make them fairly high res as well. I'll do 500 rows and columns on those. And this is going to help ensure that all of the planes go all the way through our geometry. I know it looks a little bit excessive, but we can trim this down a bit after generating those grids. So let's use our input geometry to create a bounding box for the area that we're interested in. So let's just drop in a bound and connect our fracture piece to that. And then let's transform our bounding box a bit to make that a bit larger. So I'll drop in that transform SOP and select our centroid transform preset once again. And we'll turn up our uniform scale here. And because we're going to be adding a bit of extra noise to these cutters, we want to make sure that we're not trimming these cutters too close to the piece here, because once we start adding noise, then you might start to cause some issues where the cutters don't travel all the way through the surface if the noise kind of pushes them inside the surface to only cut part way through. It's very important for these cutters to travel all the way through the surface of the geometry they're cutting, and many of the fracture problems that you may run into are caused by some little areas where the fracture cutter doesn't pass all the way through the mesh. I know that I've said this a few times over, but it's very important, and I see this problem all the time, both in my own setups and other setups that I look at, where there's some little region where you don't realize that some fracture cutter has only gone part way through the mesh. So now that we have a bounding box for the area that we're interested in here, let's group the points in our cutters that are within that box. So I'll drop in the group SOP, connect the copy to points to that, and our bounding box to the second input. The group type has to be points. I'll call this contained. Turn off the base group, turn on bounding regions, and the bounding object. So now this is only selecting the points of those cutters that are near the piece that we're fracturing. Then we can drop in a blast SOP, select the contained group, display that, and flip it to delete non-selected. And now that we've done this optimization, we don't need this contained group anymore. So I'll drop in a group delete and remove that contained group, because it's always nice to keep the attributes clean whenever we're doing our fracturing. So now that we have our trimmed down cutters, we can subdivide those for a bit more detail. I'm just going to leave this on one subdivision. But of course you can play around with balancing the original resolution of your grids versus subdivisions later, and you can add this mesh resolution at different points in the process. So now let's drop in a mountain sop once again to add some detail to these cutters. And I'm going to start out with a fairly large element size. I'll do 40 for the size and the height. And this is starting to illustrate a problem with just applying a mountain noise like this. So if we turn down this mountain noise here, you can see that these cutters that are nearly parallel with each other are getting the same shapes applied to them by the noise. So you can see that these two cutters in particular are both pushing in the same direction, and we want more randomization than this in what the noise is doing for that mountain sop. So we can run this noise in a loop here. So let's type in for each and select for each connected piece. And this will create a connectivity here, which is going to determine each of the unique pieces in our input. Let's connect that connectivity to our subdivide and move our mountain inside there. And now with this connectivity based for each loop, it's just going to process each of the grids individually. And this will allow us to set a different offset on each of the grids as the mountain noise is applied. So to set a different offset on all of the grids, one way to do this is to select the for each begin node, and then you can click this create meta import node button, and this will add this extra node with for each loop metadata on it. So if we look at the spreadsheet for this metadata node here, we're not seeing anything on points because this isn't really geometry here. But if you go to the details tab, you can see that this has information about the current iteration number that the loop is processing. It tells you how many different iterations there are. It tells you the value that it's using for the iterations. And we can use the current iteration number from that detail metadata there to set the offset on our mountain sop. Now we could, within the mountain sop here, write a little expression that points to this for each begin metadata node to look up that iteration number. But one thing we can do to make this a little bit easier in terms of writing that expression is to add a spare input to the mountain sop. And to add that spare input, just go to the gear icon on the mountain here and go down to add spare input. And you'll see this adds this extra parameter at the bottom of our mountain here. And we can drag and drop any other node in our scene into this spare input parameter. And you can see that it has this little line connecting the mountain to that metadata to show that there's a relationship between them. And this is really helpful when writing expressions because when we do a detail attribute lookup for our mountain offset here, instead of typing in our detail expression and then pointing this to a specific geometry path, which gets a little bit verbose and messy, we can instead point this to input number -1, and then we can look up a specific attribute. In this case, we'll look up iteration. And the third argument to that detail function is the index of the attribute we're looking up, which is more relevant for vectors or matrices. But since iteration is just a single number, we can just put 0 for that attribute index. And you can add additional spare inputs. You can add a whole bunch of them, and they will all be referenced via negative numbers. So the standard inputs for our nodes would be referenced by input number 0, 1, 2, 3, 4, etc. Whereas the spare inputs here are referenced by -1, -2, and so on. And it could potentially break up our noise a little bit more to add that offset to the Y and Z as well. So I'm just going to right click the offset X, copy that parameter, and paste the relative references into Y and Z here also. And right now it does look like these planes are still getting pushed in the same direction, because these are fairly large cutters and we're only doing an offset value of 0 through 4 when we're processing 5 different cutters here. So we can just add a multiplier on our offset here. So on this detail expression, I'll just say 100 times that detail value. So now we're getting wildly different offsets on the noises for all of these grids here. You can see the noise directions are now truly random and you don't see parallel grids being pushed in the same direction anymore. So now that we're done applying a varied noise for each of these cutter grids, we can now delete that class attribute that the connectivity stop created. So I'll drop in that attribute delete, remove this class primitive attribute, and oftentimes I want to apply noises in multiple stages. So I like to use this first noise pass to just get the general shapes of all the cutters. And the detail in here is looking pretty good already, but it is pretty common that after getting those general shapes of the cutters that I want to add an additional mountain noise, and this one will be a higher frequency noise. So I'll display that, and this adds a bit more detail to our cutters there. That could potentially create some more interesting edges on our fracture. And for this more detailed mountain noise, because all of these grids are already fairly randomized in their shapes, I'm not too worried about doing this noise per grid like we did before. In this case, it's fine for that higher frequency detail to be applied without doing it in a loop like we did with the lower frequency detail. So now we're just about ready to start running some fractures. And generally, I like to always add normals to my cutter grids before running the fracture. And now let's drop in a new Boolean fracture SOP. We'll connect that back to the chunk that we're fracturing up here, and connect all of our cutters to the second input of that Boolean fracture. For this, I'm going to try leaving detriangulation on for this fracture here, because I'm pretty sure that this is going to be our last fracture process in our chain. If you think you might need to fracture these pieces again, then you may want to turn off detriangulation here. And on this Boolean fracture, I'm going to turn off the exterior group. You can leave the exterior group there if you would like, but I find it usually unnecessary to have groups for both the inside and the outside because you can generally derive one from the other. So typically I just work with an inside group here. And because I do try to keep any unnecessary attributes or groups cleaned off of the geometry, I believe I forgot to turn off the exterior groups on the previous fractures. So I'm going to go ahead and turn off the exterior group here. And on the original Boolean fracture as well, we'll turn off that exterior group and rerun this cache. It may seem like I'm being a little bit obsessive about cleaning up groups and attributes, but these destruction shots can get quite heavy quite quickly, so it's just good practice to clean these things up as you go, because all of those extra attributes and groups do take up extra data, and some of that data is just really unnecessary. So now let's display our Boolean fracture result, and it's not very obvious what our fracture looks like at this point, so let's drop in an exploded view so we can see those fracture pieces, and this is looking pretty cool. So we're going to need far more cutter planes than this for an interesting fracture, and before we start increasing resolution, just a couple more things I'd like to point out here. On this Boolean fracture SOP, we may want to, instead of creating new piece names every time, we may want to add on to the existing piece names. So when we did our previous fractures here, that generated names for each of the pieces. So when we cut out this area of interest and deleted the bottom section, this left us with a couple pieces here. It looks like we have apparently 6 pieces. If we middle mouse on this blast stop here, you can see we have 6 unique names. It's possible that some of those pieces are pretty tiny and might get cleaned up later. But yeah, sometimes we really want to preserve these piece names and just add on additional names here for all of these sub pieces of piece 1. And right now we're just overwriting all of the previous pieces with a new name. For this particular case, it doesn't really matter, but in some cases when you're fracturing more complex geometry and you want to keep track of the original parent pieces, it's very helpful to append instead of overwriting the piece names. So when I do an append, I will often change the piece prefix to have an underscore at the start of it so that it's really obvious looking at the names which pieces are a sub-piece of another. So if you look at the geometry spreadsheet, you can see piece 1 is now broken up into piece 0, piece 1, and so on. And when you get into more complex destruction workflows, having this multiple layers of fracturing information available in that name attribute can be potentially helpful. So now going back to our exploded view here, you can see that our fracture seems to be working correctly. So now we can start increasing the number of cutters here. Right now we're only using 5, so we're not getting very many pieces. And I'm going to go back to my scatter here. And you might want to try turning this up more gradually, but I'm going to go ahead and turn this up to 60 cutters. And now after turning up the number of cutters on the scatter stop there, this did take quite a bit longer to process that fracture. We had to wait a few minutes here for this fracture to complete, but this is looking very detailed and looking quite good. This is going to make for a very nice rigid body simulation. So now let's do a little bit more post work on the attributes and cache this out. So first of all, I'm going to measure the area of all of the pieces. Oftentimes we want to delete a lot of these super tiny little pieces here. We don't need to simulate these really tiny fragments in the rigid body sim. We can save that for a particulate pass afterwards, but I'm not going to filter them out quite yet. I'm going to cache this out with all of the pieces, but with an area attribute so that we can filter it later. So let's drop in a measure sop and connect that to our Boolean fracture. We'll leave this on the measurement for the area, and we can accumulate this per piece. And for the piece attribute, we're going to use the name. Let's delete the class that's in there by default. And we can test this area measurement to make sure it's working properly. Let's take a look at what the range of those values looks like. So opening up that spreadsheet and then sorting by that area value, it looks like the values range from 56 down through tiny little fractions. So just to do a test to make sure it's working properly, I'll drop in a blast sop and I'll say at area is less than 1. And delete non-selected. So this is just showing us the very small pieces, and we can do an exploded view on these tiny pieces to see what they look like a little bit better. So this helps us to just verify that the area measurement is all working correctly before we cache it out. That looks all good. And another thing that's kind of an optional step is to do some more manipulation on the inside face data for our fracture. Typically, I like working with attributes instead of groups. So I'm going to, instead of relying on the inside group that's been created by that Boolean fracture, I'm going to set an attribute instead. So I'll drop in an attribute create, connect the measure sop to that. Attribute name will be inside. Class is primitive. For the group, we're going to select the inside group, and this is going to let us write values only to the inside group there. So we're going to write a value of 1 to all of those inside faces. And because inside is just an integer, we don't need this to be a decimal float value, so let's just change that to integer there as well. And another thing that I like to do is to promote this inside attribute to find all of the pieces of our fracture that are on the inside only. So when we're viewing a fractured surface, we want to make sure that the exterior stays intact, but we can delete more pieces from the interior to make things a bit more lightweight without messing up our geometry. So to find the pieces that are entirely on the inside of this mesh, we can do an attribute promote. And then on this attribute promote, let's set the original class to primitive, and the new class will also be primitive, and the name of that attribute will be inside. And then we can use this piece attribute option to promote the attribute per piece. So for each individual piece, it's going to promote that attribute from the prims to all the other prims. And for the promotion method, I'll set this to minimum. So that means that if there's an exterior face on any of these pieces, then this minimum promotion method means that the new attribute will be set to 0, and it'll only be set to 1 if all of the primitives are on the inside. And we don't want to mess up our existing inside attribute, so let's turn off delete original and change the new name to inside only. And now we can test this attribute as well. Let's drop in another blast SOP, connect that to that attribute promote, and then display that and set the group equal to inside only equals 1. So that displays all of the pieces that are touching the exterior of the surface at all. And we can flip that to delete non-selected to find all the pieces that are entirely on the inside of that geometry. And now that we have attributes for the inside data, we don't need the group anymore. So I'll drop in this group delete, connect that to the attribute promote, delete that inside group there. And now we can pack all of this geometry. But as I'm displaying this data here, I'm also seeing some unconnected points, which is a little bit of a red flag. So if there are disconnected points in your geometry, you probably want to clean those up. So let's drop in a clean SOP, and perhaps we want to do this cleanup before we do that other attribute processing there. So I'll drop this right after the Boolean fracture. And on the clean SOP, I don't want to remove degenerate primitives because sometimes that will remove some valid polygons that just happen to be quite small. So turn that off, but we'll leave on this remove unused points option. So now you can see we no longer have any disconnected points in our data here. And now the geometry looks all good, the attributes look all good, and now we can assemble this into packed geometry. So drop in an assemble SOP, and I'm going to turn off this create name attribute because we already have a good name attribute on all the pieces. Let's turn on create packed geometry, and we're going to transfer some attributes onto the packed pieces. When we create our packed geometry, by default, we don't have access to most of the attributes that are on the underlying geometry, but we are interested in that area and the inside only data. So for the transfer attributes here, let's select area, select inside only. Now we have that information available on all of the packed pieces. And when we're doing destruction work, we always want to make sure we're working with packed pieces like this. Especially once we start simulating things and transforming them, moving them around, etc. It's much more efficient to work with each piece as a packed object instead of raw polygons. And that's also just what our simulation input will want. And just to help visualize what all these packed objects look like, we can drop in a packed edit after the assemble SOP here, display that. And then for the display as option, we can display all the pieces as bounding boxes to see what all of our packed pieces look like. So that's looking all good. Now we can cache this out, but we also want to bring along the constraint data that was created during the fracture. So this Boolean fracture also will generate constraints between the pieces that are touching each other, and this is very helpful for our simulation setup. So I'll drop in a null, connect the second output of the Boolean fracture to that, and I'll call this constraints. And if you display that, you can see the connections between all of the fractured pieces that are touching each other. Once again, it seems like we have a whole bunch of unconnected points here, which is a little bit of a red flag. So I'm going to copy this clean SOP here and paste that in before the constraints. Once again, we don't want to remove degenerate primitives. We're only using this to remove unused points, and that cleans up our constraint results a bit. And just to take a quick peek at what this constraint data looks like, these are just polylines that indicate relationships between two pieces that may be constrained to each other. So a polyline represents a relationship between two pieces, and the point at either end of one of these lines has a name attribute to indicate what piece that corresponds to. So if you look at the spreadsheet here and look at the point data, all of these names indicate what piece that constraint is connected to. And this also conveniently stores the rest length for us. This can be useful in some cases, and you may want to do things like break constraints once they stretch too far beyond the rest length or things like that. But we don't need to get too deep into that now because we're only looking at the fracturing process at this point. So we'll save constraint discussion for later. But we do want to save out all of this constraint data along with our fractured pieces. And we can combine those together with the RBD pack SOP. So drop in an RBD pack, connect the fractured pieces to the first input, constraints to the second. And if you display that, you're only going to see your fractured geometry. By default, this RBD packed object is going to hide your constraint geometry in the viewport just for convenience. And this is going to allow us to cache out the fracture with the constraint data. You don't really want to merge them together because that's going to really mix up the attributes between your fractured objects and your constraints. It just mixes together all of the attributes between them and things get really messy, so you don't want to merge those together for caching them out, and it's kind of annoying to cache them separately. So this RBD pack is quite nice because it creates one packed object for the fractured stuff, just as a container for all the fractured pieces. It creates another packed object container just for the constraints. And at this point we don't have proxies, but you can also have a third container for proxy geometry, which we'll look at soon. Before we cache this out, let's add one more bit of data to our fracture geometry. If you remember with the static geometry that we already set up and sent to the render object, we've added some rest data so that shaders will stick to that geometry properly. So let's do the same thing on the fractured pieces themselves. So if we go down to our fracture results, we can add the rest data pretty much anywhere in here. So I'll drop in a rest position SOP, add that to our fractured geometry, and now we're all ready to cache this out. So let's drop in a new file cache here, and I'm going to call this destruction fracture. Set this to save current frame because it's just a single frame cache. Turn on load from disk, and we will save that to disk. So now we have our fracture ready for some more additional cleanup and post-processing and proxy generation that we will look at next.